Hello everyone. Okay, and this video it's just a remake video. Okay, this video a remake video for the example 10.2. Example 10.2. Where is example 10.2? Okay, okay, it's the torsional formula problem. Okay, and why I want to remake this video because there is some sign convention issue when you are calculate a torsional load in mechanics material. Okay, and I want to remake the video to unify the sign convention. Okay, because in previous last version or the video I made before, maybe there is some inconsistent sign convention. Okay, so that's why I decided to remake this video. Okay, so let's start with the example 10.2. Okay, the 10.2, the problem is that, okay, let me prepare the pen. Okay, okay, the problem is here. Okay, here is a shaft. Okay, here is a shaft, and this shaft is subject to multiple torsion. Okay, and he want us to calculate, okay, the shear stress develop at point A and point B at the AA section. AA section is here, and where is point A and point B? It's okay. Point A and point B. Let's see. This is the profile or cross section. Sorry, the cross section of the shaft. Okay, and the point A is, okay. Point A is on the outmost. Point A is at the surface, and the point B is at the interior of the cross section. Okay, so let me draw it more clearly. Okay, here is the core section. Okay, then A is at the surface. Okay, and its position A to the origin. Okay, origin is okay, and this shape is cross section is a circle. Okay, and what's the distance here? Distance is this is r 0.075, and where is the B? B is here. B is okay. It's not at the surface of the rod. Okay, it's an interior of, it is an interior. So, and the position here is 0.015. Okay, its unit is meter. Okay, okay, for when we want to calculate the shear stress. Okay, okay, we will use the torsional formula for the shear stress. Okay, when the member is subject to a torsional load, what is the shear stress? What's the formula? The formula is the shear stress. Okay, the shear stress is equal to T. It's just C or rho. Okay, okay. What's textbook? The textbook using C or rho. Let me see. Okay, the formula. What's the very moment? It's rho. Okay. Oh, TC. Oh, TC over J. Okay, TC over J. Okay, TC over J. Okay, TC over J. Okay, TC over J. So we want to calculate the shear stress at this AA cross section. We need to know the torque at this AA section, and the position A, the position A, it's C is equal to 0.075. Okay, and the position B is C is equal to 0.015. Okay, and what is a J? J is a polar moment of the area. Polar moment of area, right? Polar moment of area. Am I right? Okay, polar moment of inertia. Polar moment of inertia. Okay, okay. So, and this shape is a solid. Okay, so let's calculate the polar moment inertia at first. Okay, what's the polar moment of inertia of this cross section area? So, okay, don't forget the J is equal to pi over 32, and diameter to the power 4. Be careful, this is a diameter. Okay, so what's the diameter of this cross-section area? Okay, here is the radius. Here's the radius 0.075. Okay, so the diameter is equal to 0.15. Be careful. Okay, so that's the plug the number in there. So it's 0.15 to the power 4. Okay, don't forget the units. Okay, and what's the value? Okay, let me see. Okay, you can try to use calculator by yourself. Here, I just put a number on it. 4.968 10 to the power minus 5. Okay, 10 to the power minus m. The unit it's m to the power 4. Okay, don't forget the unit. Okay, so the only thing we did not know is we don't know is the torsion as this cross section area. Okay, to analyze the Okay, to analyze the torsion as the AA section, how to do that? Okay, we will use the similar technique like we in axial loading. Just it's called, or in the early of this class, it's called cut section method. Cut section method. Okay. Okay, so in this member, there is this member subject to multiple law. Also, we are interested in this cross section. So let me see. Okay, this is the initial problem. Okay, we just like we draw a free body diagram. Okay, here is 4.25 kilonewton times meter. And here is 3, and here is 1.25, and the section we are interested in is here. Here is AA. Okay, AA is between these two torque, right? Between the 3.0 kilonewton times per meter and 1.25 kilonewton times meter. Okay, the AA section is here. Okay, so we use cut section method. Okay, the cut section method. Okay, we just we cut here, so and then we just analyze this area. Okay, we just analyze this area. Okay, and this cut section is here. Here is 4.25. Here is 3, and here is the torque we want. Okay, and then we'll call it TAA. Okay, TAA. We call it TAA. So for the TAA, should we assume the TAA least direction or least direction? Okay. So when you do the assumption of the least internal torsion, internal torsion, internal torque, internal torsion, internal torsion, internal torsion. Okay, sorry, internal torsion. Okay, so we need to use, like what I say at the beginning of this video, we use the sign convention. Okay, the sign convention, we use this sign convention here. Okay, I think it shows this slide. The sign convention is, use the right hand rule. Okay, if your torsion rotates in this direction and use the right hand rule, it's point outwards. That means positive. Okay, and here the torsion is rotate in this direction, and you use the right hand rule, you rotate this direction, it's also point to outward from the surface. So so if the torque is outward to the surface, that means it's positive. So on the contrary, if you use the right hand rule and point into the surface, that's a negative. Point in. So for this part, if it's point into the surface, it's negative. Point outward to the surface, that's positive. Point outward to the surface is positive, and point into the surface is negative. Okay, so let's back to this problem. For the torque AA here. For the torque AA here. For the torque AA here. We use the sign convention. If we want to assume, use the right hand rule and want to point outward to the surface. We want to assume it's point outward to the surface. If it's point outward to the surface, which rotation we should choose? I think it's this one. I think this one. It's this one. Okay, let's go back to this. Um, here. Okay, here. Okay, let's assume the TAA is rotated in this direction, because this rotation, if your right hand rule is point, sorry, it's a point outward. It's point outward to this surface. Point outward to this surface. That's why we assume the TA is rotated in this direction. Okay, so that's a sign convention I want to address here. Okay, so and then if you cut section and then use the rigid body equilibrium, because the whole thing is the whole member or the whole system is in statics. That means it doesn't move. Okay, so the sigma torque is equal to 0. Okay, so the sigma torque equal. Okay, let's first look at this 4.25 torque. The 4.25 torque is this direction. Okay, in this direction. Okay, in this direction is positive or negative. Use your right hand rule. Okay, the 4.25 is rotated in this direction. If we use the right hand rule, it's point to outward. It's also point outward with respect to this surface. It's point outward here. Okay, this direction point outward with respect to this surface. So this is a positive. So this is positive. And for this torque is rotated in this direction, and rotate in this direction. Use your right hand rule. Okay, what's its direction? Use your right hand rule. Okay, it's point inward. It's point inward with respect to the surface. It's point inward with respect to the surface. So it's negative. And the TAA, we assume it's point outward to the surface, so it's always positive. Okay, it's equal to 0. So, and then you can see the TA is minus 1.25. Okay, so you assume initially the TAA is rotate in this direction, and you get a negative value. That means its real direction is here. Okay, you initially assume it's rotated in this way, but you get a negative value. That means the real situation is it rotates in this way. Okay, so this is a sign convention issue you need to notice. Okay, and its unit is kilonewton times per meter. Don't forget the unit. Okay, so we want to calculate the shear stress. Okay, for example, if I want to calculate shear stress at A is equal to TC over J. In this problem, it doesn't. It just want to calculate the magnitude of the stress. So the direction is not very important. So let's put a 1.25 here, because this problem only want to calculate the magnitude. The direction looks like the direction. He's not asking for a direction. So and don't forget it's kilonewton times per meter. So you have the 10 times the 10 to the power 3, and then this is T. And A, its distance is TC is 0.075 from the origin. Okay, and J is 4.96 times 10 to the power minus 5. Okay, and then just using your calculator, it's equal to 1.883 megapascal. And what is mega? Mega is 10 to the power 6. Don't forget. Okay, what is the shear stress at B? Okay, and in the previous lecture, we already know the shear stress is linear distribution along the radius. Okay, I think in the class I draw this graph. The shear stress distribution is linear along the radius. Okay, this is the shear stress distribute linear along the radius. So the position B, so it's a linear relationship. Okay, we know the maximum because point A is at the surface is the maximum. So we just the maximum because the linear relation. So We just times with 0.075 and 0.015, and you will get the 0.377 megapascal. Okay, so I remake the video for the example 10.2 because there's some sign convention issue. That's why I remake this video. Okay, so I also will make a remake lots of video for the torsional load. Okay, to unify the sign convention in this topic. Okay, because the sign convention in torsional load is very is very annoying. Okay, okay, I just stop the video here. Okay, and see you in another video. Bye bye.